Cool. Let's get started. So, hello everyone. Welcome to my talk on effective observability platforms and microservice architectures. So just a little bit of background on me. I'm a senior engineer at Teachers Pay Teachers. I've spent all of my career in edtech so far. So I've seen edtech change and grow many times, but I think I could speak for all of edtech when I say that no one ever expected we'd have to deal with the challenges that came from when the world went online 2 years ago. Right, so challenges I never thought I'd see in my entire career happened during remote learning times, going from 40 million users to over 100 million users on Google Classroom in the course of just a month, migrating school districts the size of entire countries onto Google Workspace and Classroom, and all the production issues that came along to support all of that. So no one was fully prepared, and so as you might imagine, this gave me an even deeper appreciation for the perils of debugging production. And so I took that experience with me, and when I moved on to TBT and focused a lot of my time on observability as a tech lead and engineer. And so this talk is a compilation of my learnings from the past couple of years, as well as my other past experience building data pipelines and developer platforms. So I like to start my talks off by providing a shared definition of the topic I'm going to present on, especially for something like observability. So let's begin there. So as much as I hate repeating words on a slide, I'm going to do it, if only for emphasis. So bear with me. Borrowing Liz Fong-Jones' definition of observability, observability is the ability to understand what's happening inside of your software systems to debug problems you've never seen before, just using the telemetry emitted by your applications. And the more important part here is actually it's not just about a specific tool, it's about the team's ability to analyze that telemetry data. So this is a loaded definition, right? It's kind of long, but there are some components here that are important to highlight. So the first is this part about being able to understand the internals of your software systems just using telemetry, which is just data that represents the inputs and outputs of your software. You most commonly know these to be like things like traces and logs, metrics, etc. And the reason for this is because the hardest and most interesting problems in software are the ones you've never seen before, right? They're the problems I saw in the midst of the pandemic when we were scaling in ways I never thought we would before, and I did not turn on notifications. You guys can ignore those. But yeah, so it's incredibly hard to predict what specific issues you'll encounter during development phase. So the better alternative is actually to equip engineers with the right data, tools, and most importantly, knowledge. Which is why this last part is what I think really distinguishes observability. So the most important part of observability and doing it well is that your engineers understand how to use telemetry to figure out how and why their applications are behaving the way it is. And this can be hard for any application, right? But it becomes infinitely harder, right, as our applications grow in complexity. Complexity makes everything harder, right? It makes building applications harder, and it definitely makes debugging applications harder. And complexity makes things so much harder, right, that we as a collective industry, right, have evolved the ways that we build applications. And so just like we've evolved the way we build applications to embrace microservice architecture, we must evolve the way we debug applications to embrace this full definition of observability. So if microservices are a solution to reducing development complexity for large applications, true observability is a solution to reducing the complexity of debugging these same applications. And so all that is all to say, microservice and observability, right, are both great solutions for navigating complexity. But there are three organizational challenges that I think pose a risk to organizations that rush into implementing microservices and observability that I think are particularly relevant to this audience. So the first, we have the very common challenge we're all aware of, which is silos and drift, right, between different teams and organizations, right, despite the fact that we're all operating in the same architecture. So one of the organizational benefits of microservices, right, is the new autonomy that engineers get to experience, right? We love the flexibility of being able to use our favorite tools, build services in the way that we think is best, et cetera. But the serious downsides of that are, right, like we lose consistency that makes knowledge transferable between teams. And this lack of shared knowledge is what leads to serious silos, right? And the lack of consistency is what leads to drift. And so with the increasing number of tools out there, right, different instrumentation techniques, et cetera, we end up in a similar situation where context is very specific to the team or service that you're working on. Now, the consequences of these silos, right, as we see often in the DevOps world, is that teams end up doing like a lot of duplicate work, right, because we end up reinventing the wheel of what we consider like best patterns or practices. And this kind of leads basically to the core problem with decentralization. You lose the advantage of ensuring that teams have a minimum bar of quality for how they're approaching their work. So next we have a challenge that engineers are obsessed with talking about. Sure, you've heard this one before, which is having the risk of multiple points of failure. So many of us have experienced the consequences of this, right, of the consequences of one microservice's failure becoming a point of failure for other services. We understand this risk, right, and we tend to plan for this risk. And the same can be applied to observability, but in a different form, which is the form of observability gaps, right? So what I mean by an observability gap is, when we risk not having the needed context for finding all the contributing factors of an issue. And that context, right, might be essential for figuring out the next steps forward, right? And as we have more and more of these gaps, right, in our telemetry, this risk only increases. And so if we're unable to determine what next steps forward are because of those gaps, right, the failures that we see in production can continue longer than they would have had those gaps not existed. So much like we need to think critically about how we plan for failure, we need to think critically about the observability gaps that might prolong its failure. And so really what's at the core of these previous two challenges, right, is like this inherent lack of certainty that's introduced, right? The autonomy that comes with decentralization means that coordination and collaboration efforts between teams are less necessary. But the danger of that trade-off, right, is that the assumptions we make along the way, and specifically the assumptions we make about how other teams are approaching observability. So inevitably, right, these approaches will end up conflicting in some way, and particularly when this happens frequently, we risk teams losing trust in each other to provide the necessary context that you need when investigating an issue. And this is not an exciting state to be in, obviously, right? There are both technical and cultural consequences in allowing this to fester. So what I'll spend the rest of this talk talking about is how do we address these challenges while preserving the organizational benefits that come with microservices, like autonomy and clear boundaries of ownership. And the answer for me here is the concept of introducing a standardized observability platform, right? And this idea of platform thinking or becoming platform forward has become super popular within microservices, right? For the same reasons we'll be talking about today, right? It helps drive a standardization to address the challenges that we just reviewed. And so going into the definition of what a platform actually encompasses, I define it as having three components: the patterns that guide us, the strategies that support us, and the stack or tools that we use. So at the highest level, we have the patterns we use to make our systems observable and understandable. In the context of a standardized observability platform, these patterns should serve this primary purpose by defining how we use standardization to address new organizational challenges while maintaining those original organizational benefits. And so the way that standardization does that in an observability platform is ultimately by standardizing the way we communicate, both in terms of how our services communicate with each other, but also how we enable our services to communicate with us, the engineers. And so going forward, I'll just refer to this pattern as having a standard communication protocol. So let's get more specific as to what this protocol encompasses and how it addresses silos, drifts, points of failures, and uncertainty. So there are three requirements here for what I consider a standard communication protocol. First is the need for standard data specs. These specs, right, should clarify the expectation of what our telemetry should look like, so that it can reduce any uncertainty that leads to silos and drift. And getting these data specs is foundational, because this is the telemetry that engineers will ultimately rely on to investigate and solve issues, right? And when this data isn't consistent, right, there lacks a level of predictability and reusable knowledge that makes analyzing telemetry easier. So to make this more concrete, we'll go through a very simple example of where logs from 3 different services but are from the same application but have an inconsistent spec. So how many people here have ever encountered this sort of annoying case where yes, exactly. When I was rehearsing this before with friends, they all cringed immediately. We were all software engineers. But this is exactly what I'm referring to, right? It's a small example, right? But I think, exemplifies like what I'm trying to get at here, right? We have the first two logs, which are basically the same. They're all of these are the same trace ID, right? But it wouldn't be easy to identify them as such because the key formats are incorrect, right? One is camel case, one is snake case. We've all seen this annoyance before. And in the last case, right, the camel case does match in the first and third, but it's not the same format anymore, right? It's just some string and then some nice JSON. And that sort of data reformatting especially like should never have to happen during an active investigation, right? That's like friction that we can proactively solve by making correct and consistent formats a table stakes pattern for observability platforms. So next we have standard context sharing. So this context sharing is governed by a set of rules for how context should be sent or propagated between services. And this is important, right, because this shared context is ultimately what allows you to directly connect or correlate related telemetry together. So for example, right, having a way to easily retrieve all those logs that we just saw. And the information that makes up this context should also be defined in that shared data spec. So really what this provides is a mechanism that services can use to comply with the standard. So again, to ground this into reality a little bit, right, we have, again, two different services, but this time we formalize the way we pass the trace ID by taking advantage of a protocol we all love and are familiar with, HTTP. And so because all of our services use HTTP, we can standardize the way we pass context by always inserting this information into the headers. And lastly, we have well-defined interfaces. So these interfaces tend to serve three primary use cases. The first is collecting the telemetry data from a software component. So for example, a tool that would have collected those logs to begin with. Two, processing the telemetry data, right? These might be separate interfaces. They're likely separate interfaces for things like the reformatting that we saw, and then exporting it to other interfaces. And then three, actually analyzing that data. And these are more like end-user facing applications or tools that we use. So things like Datadog or Honeycomb, et cetera. So I do have a lot more to say about this point, but I'm going to leave it for later when we talk about the observability stack portion. Cool. So now that we've gone into some of the patterns let's revisit our definition of observability actually. So earlier I said what distinguishes observability is this highlighted part, right? About how it's not really about how your telemetry tools, it's about your team's ability to analyze that telemetry. And so far we've talked about the patterns that drive standardization, and like in an easy, perfect world, right, we would set these standards, build tools to support these standards, use the tools, right, and just become like really awesome at debugging production, right? But if you've ever built software, it's never usually that easy, right? I think one of the core themes of the conference that has emerged, right, is like, I think Nate said in the opening talk that people problems are some of the hardest problems. And I think this is definitely relevant here too, right? The hardest part about observability is building those skills to get good at debugging production. So yeah, I think for us, right, as people who are more on maybe the platform side or cloud ops side, whatever, we have to start thinking instead about like how do we make sure that teams have the skills to even use our platforms effectively, right? We have the tool, we have a platform, but like how do we make sure that engineers are actually using them effectively? So to address those challenges, that's why I define platform support as a second component of our platform. Because a platform without adoption or engineers without the skills to use that platform might as well be a platform that doesn't exist. Cool. So before we head into the strategies guiding our platform support, just going to acknowledge, right, like building observable applications requires investment, right? Investment in time, resources, et cetera. And telemetry isn't just given to us for free, right? We have to think about observability as we're developing our applications instead of just afterwards, which is, I think, a pattern I've seen way more common than it should be. And so having been on many product teams before as well, I understand like the difficulty, right, in prioritizing this work. It's super easy to devalue when you're deciding between like working on, as a product engineer, working on making logging better over, a shiny new feature that your users might really love. And it's mostly we come to regret this when we're like in the middle of an incident and we haven't invested time, right? And I think this tension is why we have seen a lot of microservice organizations come to embrace this idea of having separate platform teams. And this organizational pattern, I think, does align well with what we're talking about right now. Right? It does make the effort to standardize easier, right? If you have a team dedicated to doing this work more full-time instead of having to coordinate efforts between multiple teams and orgs, right? But again, this doesn't save us from like the people challenges of work. Instead of having to worry about effective coordination strategies, we have to worry about effective support strategies. And so what do these support strategies look like? The most effective strategy for enabling engineers to build observable services, right, is to make it easy. Not controversial, but setting the standards we reviewed earlier is a huge step towards this goal, right? But we can also reuse our patterns from developing production-ready microservices to further serve this goal, right? So a common microservice pattern is to standardize the way that services are built so that it's easier to build production-ready services, right? You see this most commonly through like org-wide templates or libraries, right? And you can apply the pattern here too. Well, oops, sorry, missed a point. And I think the biggest benefit of this, right, is like the more that we as platform teams take on the implementation details that product teams would have to take on otherwise, right? The more we can make sure that teams are following those standards while also freeing up time that can be spent tackling problems that can't be automated or implemented away, right? And one of those harder problems that can't be easily implemented or automated away, right, goes back to Liz's point about building up our team's ability to analyze telemetry, right? Again, this is the most important part of observability. And this is why the time we save by consolidating efforts to build the tools that support us in analyzing telemetry is so crucial, because the biggest investment organizations can make with respect to observability is providing engineers time to invest in their skill set, right? And I know defining what support can look like is very challenging, but I think one of the best things I've ever done to support the teams I've led was to standardize on-call training and what actual on-call looks like, et cetera. And so lastly, on this component of our platform, we have what I think is the most effective long-term strategy, which is to work on embedding observability into your culture, right? As folks who are on the DevOps or site reliability engineering side, right, I think this is like an incredibly important tactic for us to use, right? Fundamentally, this means constantly reinforcing the idea that observability is a crucial part of what it means to manage production services. Right, the strategies we just talked through, right, lay some foundation for that, but there are plenty of other ways that we can reinforce this, right? So cultural change tends to happen in two ways, right? Top down, bottom up. And when executed together, right, these approaches become super effective for driving prioritization. So for those of us who are some sort of engineering leader, whether that's a manager or a tech lead or staff engineer, et cetera, right, we can take on this work of driving top down and bottom up change. For me, right, that's meant working with my engineering peers and cross-functional partners to get their buy-in. And luckily for us, the industry has already thought about how to do this effectively, which is why I spent a lot of my time at TPT driving the adoption of SLOs, or service level objectives. I'm not going to go into the details of this work too much because it could truly be its own separate work, but the important takeaway here, right, is that SLOs provide a clear decision framework that makes it easier to hold your culture accountable to your reliability needs. Cool, so now that we reviewed the platform and support patterns guiding our observability, we can start to talk about how these manifest in the way that we build the actual tools that make up our observability stack. So what even is an observability stack, right? What's the purpose? So an observability stack is the collection of interfaces or tools that facilitate service to service and architecture to engineer telemetry communication. So if you remember the interface pattern from earlier, it introduced this idea that separate concerns should be handled by separate interfaces, right? I briefly mentioned the use cases then, but just to reiterate and put them into a larger context, let's review them once again. So, right, again, the goal is to facilitate communication between our architecture and ourselves, the engineers. So our architecture our architecture uses standardized communication patterns to generate telemetry, right? And our tools, the end user facing ones I mentioned like Datadog or Honeycomb, receive all that telemetry so that we have access to it as needed. And so how do we go from generating our telemetry to actually receiving it? And the answer, right, is like we do need some layers of abstraction to facilitate this, right? And so I'll refer to this roughly as the communication layer of our observability stack. And so there are plenty of different design decisions that you can make in terms of how you split or separate the interfaces that make up your communication layer. But I'm going to use my data eng background here and split it into 3 phases that roughly correspond to the ETL pipeline. And for folks who are unfamiliar with that acronym, right, ETL just stands for extract, transform, load. We'll use collect, process, and export instead, though. Cool. So yeah, this first part, as I just said, there's three portions that each roughly correspond to the ETL pipeline. So the first, right, just instruments telemetry from your architecture. The second portion, right, is like it further processes the telemetry, right, to comply with data standards. And lastly, right, it actually exports telemetry to the end user facing apps. Cool. Oops. Yeah, so these are just the 3 different parts of our communication layer. Now we'll focus our attention back to talking through some patterns that we should apply throughout this pipeline. So first, let's talk about 2 important design principles that should guide our stack. All right. So, right, the first is that our communication layer needs to be reliable. So in addition to the actual data pipeline being reliable, reliability here also means the telemetry data itself needs to be reliable. And so this means in addition to like minimizing data loss and duplicate data, right, we want to make sure that the data is accurate or complete. And completeness should always be defined by our standards that we talked about earlier. The next design principle we have is richness, which expands how we think about telemetry to include an added flexibility that allows us to collect data specific to the service and environment that it's being emitted on, right? I kind of talked about this point a little bit earlier, but part of defining specs for our telemetry is also defining how telemetry should emit service-specific data. And so the reason this is so important, right, is because it's how we solve unknown unknowns, right? It's not always clear what data may or may not be relevant during an investigation, so we should generally try to bias towards collecting more information that can't be found anywhere else or reasonably approxied. So that basically means embracing high dimensional or high cardinality data instead of being scared of it. So what do these design principles actually look like in practice? So I'll review 4 best practices you can use to build what I think is a robust communication layer. So the first has us going back to the first pattern we talked about, which essentially asks, like, what's our shared definition of telemetry, right? I posed this question, and why asking this question is so important, but I didn't really give an answer outside of a vague reference to the fact that traces, logs, and metrics are a thing that exist. And so what I'm about to say isn't anything new, but it is important, which is that whatever shared definition it is that your organization comes up with should be driven by event-oriented model of telemetry, where an event is basically one singular unit of work. And this is because being driven by events rather than being driven by traces or logs or metrics removes the limitations that we traditionally place on ourselves by caring about one of these things more than the other. So in an event-oriented world, the best insights we get from analyzing telemetry data are the insights we get from piecing these things together in different ways, as different ways of interpreting a telemetry. So in other words, right, it becomes less about a singular log or metric and more about like, here's a thing that happened, or event that happened, and how can I use my trace data, my logging data, and my metrics to figure out what, why, and how this event even came to be. And this flexibility, right, is something that we don't always give ourselves when thinking about observability, right? We see traces, metrics, and logs as traditionally very different things when they're really not, right? They're just different representations of the same information. So now that we have some solid definitions of telemetry oriented by events that we can fall back on throughout our pipeline, let's talk more about how to enforce more reliability and like rich data again. So what's our next step forward, right? Instrumentation. And again, we see the influence from a standardization pattern earlier here, right? The biggest benefit of standardization, right, is the certainty that it gives us. And when we talk about our data needing to be reliable, what we really mean to say is that we need to be certain of what it's going to look like. And so since instrumentation is ultimately what creates our telemetry, it's important that the way we instrument our telemetry is consistent. That way we have a baseline understanding of how we can expect all of our events to look like, which brings us back to this, which brings us to the next two best practices, which is that auto instrumentation should always be your first strategy for instrumenting your applications, because it's the best way to ensure consistency. Now, I did include a little bit about manual instrumentation as a fourth, because sometimes you will need manual instrumentation, right, to annotate context that's specific to your architecture. But generally speaking, right, like this should be complementary to auto instrumentation instead of replacement. So that wraps up the best practices of our communication layer. So what we're left now with is the tools that end up receiving all this data so that engineers can go ahead and analyze it. So when it comes to this part of our observability stack, most of us rely on external vendors for these tools. So I've mentioned Datadog and Sumo Logic, et cetera. Most of us aren't building our own homegrown observability tools. So instead of focusing on design patterns like I did in the last section, I'll just focus on a few criteria patterns we can use to inform how we choose our tools. So when it comes to choosing tools, both generally, but I'll of course focus here on observability, I think of it as an exercise of managing complexity. We already have to learn so many tools. We should always be purposeful about like introducing a new one, right? So what does this purposefulness look like? The first and I think most obvious, right, is like what gap does it actually fill? We want to have access to functionality that is going to enable us to debug, but we want to be careful about introducing redundancy, right? Both in terms of functionality, but also in terms of like introducing multiple data sources to reference. So the consequences of redundancy right here is that like you have multiple sources of data that could have conflicting information, and you could have multiple ways of doing the same thing, leading to diverging practices, right? And this is the point of view that you should always be starting from when doing any tool evaluation. Secondly, right, how compatible is it with our platform vision, the one I just laid out here for you all? Right, how compatible would it be with your core architecture and your observability stack, right? Would it require us to take on more complexity by building new interfaces, or could we reuse existing collection processing or exporting tools? And like, if we do have to introduce new tools, right, would these be reusable by future tools that we might want to adopt in the future? Or are they like vendor-specific tools? And then thirdly is how easy is it to use, right? Developer experience is always important, right? But it's especially important when it comes to the tools you use to debug in production, right? Bad tools, I'm sure everyone can think of a bad tool right off the top of their head, right? They're annoying, period. But there's nothing more annoying than a bad tool when you're in the middle of an incident and stressed as hell because you can't figure out what's going on because you're too busy fighting your tools, right? So ease of use, right, can be many different things, but some of the things I tend to look for is like, how easy is setup, right? Is it easy to query data, et cetera? And lastly, we have developer support. So I said this earlier, and I will happily say it over and over again, right? Platforms or tools without adoption or engineers without the skills to use that platform might as well be tools that don't exist, right? And the level of support that your organization, right, might need can be very situational. For example, like at TPT, I know this idea of event-driven telemetry was a new one for a lot of folks, right? And so it would be unreasonable for me to expect everyone to suddenly shift towards this new framework of thinking. And even if I think I've done a decent job of evangelizing these ideas, right, it's not something that has to be done alone. So before treading into like the rabbit hole alone, consider like what actual support around a tool is available. And this doesn't just refer to like the specific support provided by a vendor you're considering, though of course that's an important part of it too, but also like how's the developer community around them? Which transitions me to my last and final point / anecdote. I think it's a really exciting time for the observability space. There's so many minds and communities thinking about this stuff super deeply, and there's so much to learn. So I think for me, right, don't try to learn this all on your own. Learn and contribute to the communities doing this work. Because as much as the strength of your observability is about your team's ability to analyze telemetry data, the strength of your observability is also about our industry's collective ability to learn together and make progress together. Thanks.